Hi everybody, I hope this video finds you well. In today's video, we're going to be finishing up our discussion about the sampling distribution and the central limit theorem. So far, we've done sort of two major things with this. We've introduced you guys to the concept of the sampling distribution and learned how to work with the sampling distribution using the central limit theorem. And then we also did several examples where we had normally distributed populations and we were able to calculate a variety of different probabilities based on our knowledge from earlier on the normal distribution, as well as that mixing with our knowledge now of probability and also the sampling distribution. So, before we get into some examples with some non-normally distributed populations, let's go ahead and just review quickly what the central limit theorem tells us. So, central limit theorem, remember, tells us what to expect about the sampling distribution of samples of size n based on our population. So we've got our population with mean mu and standard deviation sigma. We are looking at the sampling distribution of samples of size n. So remember, that's telling us about what we expect to see for the average of a group of size n. And we learned three sort of important facts. First, the mean of the sampling distribution is the same as the mean of the population. The standard deviation of the sampling distribution is the original population standard deviation divided by the square root of n. And the shape of the sampling distribution will be more normal than the population. We broke that down into two subcases. Last video focused on this subcase where the original population was normally distributed, so the sampling distribution was also always normally distributed. Today's video is going to be focusing more on this subcase where the original population is not normally distributed, but the sampling distribution will be approximately normal as long as we take samples of size 30 or more. So those are the three main components of the central limit theorem. Let's look at a couple examples here. All right, so for our first example here, we're going to suppose you're studying the number of tickets sold to each performance at a theater. So we have this information that the theater has a maximum occupancy of 500 people and it often sells out. So it often sells out all 500 tickets for each show. We also know that the average number of tickets sold per show is 485 and it has a standard deviation of 30 tickets. So we're going to do a couple things here. We're going to first determine what is the most likely shape for the distribution of the number of tickets sold per show. Then in part B, we're going to consider what happens during an entire season of performances, and we're going to suppose that each season consists of 50 shows. So we're going to describe the sampling distribution for samples of size 50 to sort of understand what should happen not on each individual show, but during a season of 50 shows. Finally, we're going to calculate some probabilities. We're going to calculate the probability that during a season, or 50 shows, the theater averages more than 490 tickets sold per show. And we're also going to calculate the probability that the theater averages less than 475 tickets sold per show. Finally, we'll do something that'll be a little bit new. These two should be pretty standard because they have the word average in them. So we know it's going to be a direct application of the sampling distribution. But part E will be a little bit different because it mentions not the average, but we want to calculate the probability that during the show, or during the season, the 50 shows, the theater sells more than 24,000 tickets in total. But we'll see how we're going to be able to phrase that in terms of an average. But let's start naturally enough at the beginning and talk about the most likely shape. So why is this even part of the question here? Why are we being asked about the shape? Well, if you look at the crucial information here, as normal, we're told the average, 485, and we're told the standard deviation, 30. But normally we get a third piece of information. Normally we get to know that the distribution is normal, but there's no mention that the number of tickets sold is normally distributed. So the very first question we're actually going to ask ourselves is, what is the most likely shape? Now you can do this way back from when we sort of did this around the sort of beginning of our class. And we talked about how you can a lot of times figure out the most likely shape using some common sense and also using the sort of average value, the standard deviation, and any sort of boundaries that might exist in the data. So let's think about in what we have in this case. So for part A here, right? The most likely shape, well, what are our options? Well, for this class, we've learned four shapes: left skewed, right skewed, Bell normal, and uniform. Well, keep in mind that we know that the average is 45. And we also know that they can't go beyond 500 because they have a maximum occupancy of 500. We also know that they often sell out. which means, right, that a lot of the individual shows will have really high numbers of ticket sales. So they'll often sell 500 tickets or close to 485 tickets. So if we're sort of imagining this as a histogram, right, there's our sort of values of our variable, right? So this would be tickets sold, and this would be frequency. Well, remember, they can't go beyond 500. And obviously, I guess they also can't go below 0. But we know that they often sell out and that the average is 485. So that means that the bars over here, sorry, that's an ugly looking bar there, right? The bars over here have to be very tall because the average has to land over here, and we also know that they often sell out. They often reach their maximum. So the only room for a tail is on this direction. So what sort of shape are we looking at here? Well, this guy looks like it's going to be most likely left skewed. So the individual ticket sales, right, the ticket sales per show is most likely following a left skewed distribution because they often sell out or near a maximum capacity, and maybe very infrequently they sell significantly less than that. So this would be most likely left skewed. Now remember, since we don't have access to the raw data, this is only a guess, but it is the most likely guess. No other shape that we've discussed really makes sense because with that 485 being so close to the upper end of 500, there's no room for a tail to the right, and there's no room for a bell shape because you can't even go a full standard deviation above the average before passing that sort of maximum capacity. So it's most likely left skewed. Now, why am I taking so much time to talk about this shape? Well, because unfortunately, when things are left skewed, we're pretty much stuck. We don't have a good way of working with distributions that are left skewed. We know how to work with distributions that are normal. That's where we can use the z-score and that table A. But if something's got a different shape, we're sort of stuck. So notice that the remainder of this question isn't going to ask about ticket sales of a single show, because those single shows follow this left skewed distribution that we don't know much about. Instead, as part B sort of asks about, we want to focus on seasons that consist of 50 shows. So let's see if we can describe the sampling distribution for samples of size 50. Okay, so for part B here, we want to do the sampling distribution. And since we're doing 50 shows, we have n is 50. So since we're asked to describe, we need to talk about the center, the spread, and the shape here. So let's think about the center. That's going to be our average. Well, according to the central limit theorem, right, the average of the sampling distribution is the same as the average of the population. So in this case, that was at 485. So if they sell 485 tickets on average per show, then they should also average 485 tickets over 50 shows. So the average would be 485 tickets. What about the standard deviation? Well, we know that the original population standard deviation was 30, but since we're doing a sample of size 50, the central limit theorem tells us that the new standard deviation is going to be 30 divided by the square root of 50. The original standard deviation divided by the square root of the sample size. If you pop that into your calculator, right, what you should get there, let's see here. We get 30 divided by square root of 50. And you should get that that's approximately 4.24 tickets. Okay, so while single shows have a variation of about 30 tickets sold, a group of 50 shows should only have a variation of about 4.24 tickets. So much less variation because it's a pretty large group or pretty large sample. Okay, what about the shape? Well, we know that the original population was left skewed, which is sort of why we're unable to work with individual shows, because they follow this left skewed distribution. But what does our central limit theorem tell us? Well, our central limit theorem tells us that the sampling distribution is more normal. And specifically, if you go back to that third component, it says even if the original population is not normally distributed, the sampling distribution will be approximately normal for n greater than or equal to 30. So in our case here, well, we can just simply say, since n equals 50, which is definitely greater than or equal to 30, this implies that we're going to have a normal distribution. So, in other words, while individual shows might follow a left skew, groups of 50 shows, or what we're calling a season in this case, are actually going to follow a normal distribution with a mean of 485 and a standard deviation of 4.24. Now we're able, when we're working with groups of 50 shows at least, to use our sort of table A and our z-score method because we know we have this normal distribution. So let's go ahead and do that, trying to do this part C. So we want to calculate the probability that during a season, the theater averages more than 490 tickets sold. So for C, we want to calculate probability. So group of 50 shows, average above, what did we say there? I think we said 490. Okay. All right, notice again that word average, that's always our tip-off that we should use the sampling distribution, and of course we have all the relevant information there. So we have our group of 50 shows, so we're using this n equals 50 sampling distribution, and we want the average to be above 490. Since the sampling distribution is normal, I can go ahead and draw my bell-shaped curve. Oh, that's a horrendously bad-looking bell-shaped curve. There's my bell-shaped curve. Okay. Put the middle at the mean, which in this case is 485. So there's 485. 490 is a little bit above that, so we can put 490 over here. And we want the probability that it's greater than 490, so we will shade in to the right here. Okay. All right, now we can go ahead and calculate our z-score. Z is the observation, which is 490, minus the mean, which is 485. Divided by, well, the standard deviation. Of course, we're talking about a group of 50, so we use the standard deviation that's associated with that group of 50. So that would be 4.24. And if we do that, looks like up top we should get 5. And then we take 5 divided by 4.24, and looks like our z-score should be 1.18. All right. Then we can go ahead and find that on table A, which I believe is at the end of this document. So let's go ahead and just grab that real quick. So there's table A. We were looking for 1.18. So there's 1.1 and then 0.08. Looks like it's right there. So we get 0.8810. So let's go ahead and record that. Okay, 0.8810. All right. Is that our shaded area? Well, we know that the table always tells us what's to the left, so that's 0.8810. So in this case, our shaded area would actually be 1 minus 0.8810, which looks like it would come out as 0.1190. There we go. So that tells us that the probability that a group of 50 shows average above 490 tickets sold per show is 0.1190. So in other words, what this is really saying is that there's about a 12% chance that during one of their seasons, they average more than 490 tickets sold per show during those 50 shows. Doesn't mean that every one of the 50 shows is going to sell more than 490 tickets. It's saying that the average number sold during the course of that season, during the course of those 50 shows, will be above 490. So the idea here, right, even though computationally it's pretty much the same thing we've been doing, is that the original distribution is not normal. So we're not able to ask or answer questions about individual shows. But we can answer questions about groups of shows because we know that those will follow that normal distribution. Okay, let's go ahead and take a look at how to do D here. So for D, we want to calculate the probability that during one of these seasons, the theater averages less than 475 tickets sold per show. So let's go ahead and do that on the next page here. Okay, so we'll just zoom in a little bit. Okay, so for D here, we want to do probability group of 50 shows, average less than 475. So same idea, we know it's about an average, so we know to use the sampling distribution, and we're going to use the same one we've already built because it's a group of 50. So we draw our bell-shaped curve. The middle is still going to be at 485. 475 is going to be somewhere over here. And since it says less than 475, we're going to be shading in this little portion over here. Okay, now we can go ahead and get our z-score. Z is going to be the observation, 475 minus 485, divided by that standard deviation. And of course, again, we're going to be using the standard deviation that applies to groups of 50, which is at 4.24. So let's go ahead and use that. So we'll have 4.24 there. And that means, looks like we're going to get negative 10 up top and then divided by 4.24. Looks like that should come out as negative 2.36. Okay, now we've got our z-score. We can look that up on our table. So let's go ahead and do that, negative 2.36. So there's negative 2.3, and then we need the 6 here. So it looks like we should get 0.0091. So 0.0091. Okay, so let's go ahead and do that. So we look up that up on table A, and we found 0.0091. Does that actually match? Well, table always tells us what's to the left, so that stuff there is 0.0091. That tells us that the shaded area in this case is exactly what we found on our table, so 0.0091. And that tells us that the probability that a group of 50 shows average less than 475 equals 0.0091. So if you think about that, the chance that a group of 50 shows, or that an entire season of shows, averages less than 475 tickets sold per show is a little less than 1%. Now, this is a good moment to sort of tell you guys why we're bothering to do all these computations. If you think about this, what this is really saying is it is extremely unlikely, less than 1% of the time, that a season of worth of shows would average less than 475 tickets sold. So what if we did have a season that averaged less than 475 tickets sold per show? Well, we could make the argument that we just got unlucky, right? That we just observed something that's supposed to only happen 1% of the time. I mean, that it can happen, so maybe we're just unlucky. Or maybe we would be very concerned that that tells us that our assumption that we normally sell 485 on average wasn't actually correct. And that's where we're going to be headed with all this stuff when we start into hypothesis testing in our next set of videos, is to argue that something really unlikely like this, if it were to happen, might tell us that our original assumptions are incorrect. Now, we're not quite there yet, so we're just assuming that all the information we're being given is correct, but that is where we are headed with our inferential statistics. All right, we had one last part to do on this guy before we try our second example. The second one, or the last part of this that we wanted to do was a little bit different. We want to calculate the probability that during a season, so still 50 shows, the theater sells more than 24,000 tickets in total. Now, obviously, this is a sort of different size of number. 24,000 doesn't really mix with 485 and the other sort of information we have here. So we sort of have to recognize that we've got to translate this question into something that makes more sense for us. So let's see how to do that. So just to rewrite it here, for part E, we want to get the probability that a group of 50 shows have a total, I think we said above, 2,400 or 24,000. Okay. So our idea is to translate from total into average. So the idea here is that a total of 24,000 over 50 shows is equal to an average of 24,000 divided by 50. So in other words, what we're saying is if this is the total that happens over 50 shows, then that's the same as the average of that total divided by the sample size. And if you do that in your calculator, 24,000 divided by 50, that's 480. So in other words, the actual question we're going to answer, which is the same, is we're going to get the probability that a group of 50 shows have an average above 480. So we're going to not answer this question. We're going to answer an equivalent question that is based on something we know how to do, dealing with the average. Now, you might be a little unsure about why this is actually true. Why can we convert from a total into an average? So I just want you guys to take a little thought experiment to make sure you understand this. Imagine that you and a couple other people, maybe you and 4 other people, so a group of 5, are going to go somewhere, and when you get there, you need to have $100. You need to have a total of $100 for those 5 people. What that means is that on average, each person needs to bring $20 because 100 divided by 5 is 20. If everybody can bring on average $20, you put all your money together, you'll have a total of $100. Now, why is it an average? Well, if you only bring $10 and somebody else brings 30, your 10 and your 30 can combine and they can cover for you. So this doesn't have to be everyone getting above 480 or everyone bringing $20. It just has to be an average. So in other words, just remember that anytime you see a total, it can be translated into an average via division. So now we can do this our standard way. So we draw our bell-shaped curve. We put the middle at 485. 480 is a little lower than that, so over here. But we want the sales to be above 480 on average, so we're going to be shading in to the right here. Then we can go ahead and calculate our z-score. So it's going to be 480 minus 485 divided by the standard deviation that applies to groups of 50, which in this case is 4.24. And if we do that, we're going to get negative 5 divided by 4.24, and you should get negative 1.18. Okay, let's go ahead and look that up on table A. So negative 1.18. We'll do that right here. Negative 1.1. There we go. And, well, I guess we can zoom out a little bit to make that a little bit easier. There's negative 1.1. 108 should be right there, so 0.1190. So we'll go ahead and put that over here. So we get 0.1190. So the stuff this way is 0.1190. To get that shaded area, all we need to do is do 1 minus 0.1190, which looks like it's going to give us 0.8810. So what that tells us is that the probability that a group of 50 shows average above 480 is 0.8810, so about an 88% chance. And that means that the probability that a group of 50 shows have a total above 24,000 is the exact same thing. And you don't really need to rewrite this because these two things mean the exact same thing. But this is just to remind you, we don't actually solve this. We solve this relation about the average here. Okay, so this was an example showing you guys that you can use our standard methods provided that you're working with a large enough group to ensure the normality. Let's look at one more quick example similar to this. All right. So in our next example here, we're going to suppose that you're studying the number of books read by American adults per year. So you find a study from 2016 that reports that the average number of books read per year was 11.9 with a standard deviation of 12.2. So let's think about what is the most likely shape of for the distribution of number of books. Notice once again, we're given two core pieces of information, the average and the standard deviation, but we are not told anything about the shape. That's why it's a natural question that in part A, we're asked about the shape. So let's think about what the most likely shape is here. Most likely shape. Again, you can sort of think about a little mini histogram. So this is number of books, and this is the frequency. Okay, now, are there any bounds on this? Well, you certainly can't go any lower than 0. And we know that relatively low values, like around 11.9 or so, should be pretty frequent. So in other words, we should expect some tall bars in here. Right? Now, we might argue about whether or not it's really frequent that a lot of American adults don't read any books or something. So maybe we can just put sort of a moderately sized bar over there. Now, what about over here? What about the frequency of people who read tons and tons of books? Now, certainly there's going to be some of them, but they're not going to be very frequent. So what sort of shape are we drawing here? Well, this guy is going to be right skewed. So what we're saying here is that the most likely shape, again, without access to the data, we're just making a guess, but based on this information, the most likely shape for the number of books read is right skewed, because lots of people will be at the low end, and the only room for a tail will be out to the right. Okay, so once again, we're sort of stuck because it's right skewed. We're not really able to answer any questions about individuals here. Luckily, though, as you can sort of see in the later questions, we're not going to be interested in individuals. We're going to be interested in groups of 100. So before we get to those, let's talk about the sampling distribution for samples of size 100. So to do that, we want to talk about the sampling distribution with n equals 100. So let's go ahead and do that. So what is the mean going to look like? Well, according to the central limit theorem, mean shouldn't change. So the mean up here was 11.9. So that'll be the same here. So it'll be 11.9 books. Standard deviation, well, it'll be the original standard deviation, 12.2, divided by the square root of the sample size. So it'll be 12.2 divided by square root. In this case, we're talking about groups of 100. So divided by the square root of 100. That'll come out as 1.22 books. All right, what about the shape? Well, the original shape is right skewed, but we're taking a sample of size 100. So n equals 100, which is greater than 30, implies that it's going to be a normal distribution. So the sampling distribution is going to follow a normal distribution with an average of 11.9 per 100 people, and it's only a standard deviation of 1.22. Okay, now we're ready to start calculating some probabilities. So first one we want to do is that in our sample of 100 adults, the average number of books read per year was less than 9. So for C here, we want to do the probability group of 100 has average less than 9. Once again, word average in there, tipping us off that we're going to be using this sampling distribution. Did we build the correct one? Well, it says group of 100, so we want to use this guy right here. Okay, so we can go ahead and do this, draw our bell-shaped curve. We can put the middle. Well, where should we put the middle for this? Since it's a group of 100, the mean here was 11.9. So 11.9. The observation is 9. So that'll be somewhere over here. And we want the average to be less than 9. So we can put this over here. Okay. We can go ahead, get our z-score. Observation 9 minus mean 11.9 divided by standard deviation. Make sure to use the modified one. So 1.22. And up top, you should get, let's see, 9 minus 11.9 divided by 1.22. Looks like that should come out as negative 2.38. So there's our z-score. We will look this guy up on table A. So negative 2.38. There's negative 2.3, and the 8 should be right there, so 0.0087. So we just found 0.0087. That means this stuff this way will be 0.0087. That does match our shaded area. So the shaded area here is 0.0087. So that tells us that the probability of a group of 100 adults having an average less than 9 is only 0.0087. So that's about 0.8 or 0.9 of a percent. So very, very small. So again, let's think about where we're going to be headed with this sort of information. So again, if you actually read this information and you said, okay, 2016 average was 11.9, standard deviation was 12.2. Maybe you say, okay, it was 2016, so maybe things have changed. You take your own sample, you happen to select 100 people, and you find out that the average was less than 9. So out of the 100 people you actually talked to, their average was less than 9. Again, you could sort of say, well, maybe I just happened to get really unlucky. Maybe my sample just happened to be a lot of people that don't read books. But you're again sort of saying that you happen to witness something that's supposed to happen less than 1% of the time. The other explanation, of course, is that that average is no longer 11.9 and has actually moved lower, meaning that this could be used, a group of 100 people that has an average less than 9, as evidence that the average is lower than 11.9. Again, we're not quite there yet, but I just want you guys to sort of think about that's the logic we're going to have in the next few videos. All right, we have one more computation we wanted to do here. We wanted to calculate the probability that in our sample of 100 adults, they read more than 1,100 books in total. So just another example using the total here. So let's go ahead and do that. So what we want to do here is we want to do for D, the probability group of 100 adults have total above 1,100. So once again, we see that word total, so we need to convert. Let's go ahead and do that. So group of 100 having total 1,100 is equal to a group of 100 having average 1,100 divided by 100, which is equal to 11. So we can rewrite this question not in terms of total, but in terms of the average. So we can say we want to calculate the probability that a group of 100 adults have an average above 11. So if our group of 100 adults average above 11 books per person, then their total will be above 1,100 since there's 100 of them. So now we can answer this question. So once again, we can draw our bell-shaped curve. The middle here, I believe, was at 11.9. Is that what we had here? Yep, 11.9 and 1.22 is the standard deviation. So 11.9. Our observation here, 11, is going to be over here. And we want it to be greater than 11. So we're going to be shading in this way. So over here to the right. Okay, we can calculate our z-score. 11 minus 11.9 over 1.22. That looks like we should get up top 11 minus 11.9 is going to be negative 0.9 divided by 1.22. That looks like we should get negative 0.74. Okay. We look that guy up on table A as normal. So we're looking for negative 0.74. So there's negative 0.7, 0, 1, 2, 3, and 4. So we should get 0.2296. So let's go ahead and do that. 0.2296. That's going to be the stuff this way. So 0.2296. Is that our shaded area? Nope. So we got to do our shaded area here. Is 1 minus 0.2296. Which sounds like it's going to be 0.7704. So what does this tell us here? Well, this tells us that the probability, again, it tells us this probability, but it also tells us the one we actually wanted. So the probability that a group of 100 adults have a total above 1,100 is equal to 0.7704. And that's exactly what we wanted to calculate there. So these two examples basically show you guys how to use the sampling distribution in the event that you have a non-normal population. If you put this together with the previous video, you now can understand how to use the sampling distribution when you have a normal population and when you have a non-normal population. Our next set of videos will get us ready for the sort of big topic that remains in our class, which is moving into hypothesis testing and building confidence intervals.